Swayam Prabha. Digital India. Educated India.
Okay, now I plot it. Never plot. See, in this hydrology, the processes are happening continuously, right? Discharge, rainfall. But we are measuring it at discrete time step every 6 hours in this case. That means the process is continuous, but my measurements are at discrete time step. Then I should not connect my points in sharp lines. It should be only a smooth curve. That is why I have drawn first with what we have seen in the earlier cases, sharp line. But since the process is continuous, you can see the shape of the unit hydrograph. It looks like a triangle, but here in this case, it looks like a non-linear curve. Okay, so you can redraw other previous graphs also if it is a smooth curve. Okay, this is how to derive a unit hydrograph from a simple storm, also called as single storm event. Suppose if the storm is complex, let us take the first case, complex storm. That means it is a multiple depth of rainfall, but duration is constant. Okay, 6 hours means maybe 3 centimeter in first 6 hours, 2 centimeter in second 6 hours. That is the case A. Let us do that. Which is this case is the reverse of what we have seen. Yes, principles of superposition. Right. Now you see in this case. Now in this case, this is inverse of the problem already we have solved using principles of superposition. In this case, rainfall of varying magnitude has occurred for constant duration. Assume that, first assumption, assume that you have a unit hydrograph of d hour duration. In this case, it is 6 hours and their ordinate values are u1, u2, u3. You don't know even how many ordinates are there. Let us assume that it is continuous. Right? Now what happened? I am just first hydrograph. In this case, you see, there are two rainfall. The first discharge, which I have observed in direct runoff, is due to only the first rainfall. So this one I got by adding the discharge at first rainfall. That is only R1, U1. Whereas the second discharge, Q2, in my flood hydrograph, is due to the first rainfall, but ordinate is U2 of my unit hydrograph, and also due to first rainfall U2. For second rainfall it is U1. When I add this, that will be my second discharge. Third discharge, if suppose if I have another rainfall, that's why I gave it red color. In this case I have drawn only two rainfall. If there is one more rainfall of another R3 for 6 hours, then I go on adding. So it is nothing but how I did this graphical way, I am putting it in numerical way. So the discharge measured at any point is nothing but the algebraic sum of the rainfall multiplied with their respective unit hydrograph contribution. Okay. So this can be converted into a matrix also, right? And then solve it, right? It's a lower triangular matrix. Okay, please convert this and then check up. Now I have given an example, right? So derive a unit hydrograph from a complex storm of 5 centimeter and a 4 centimeter. Okay. Now the first discharge is due to R1 U1. Now in the first equation I am estimating the value of U1. Now in the second equation, the only unknown, I know what is R1, I know what is R2, and from the previous one I found out U1, the only unknown is U2, discharge is also. So that means by substituting the previously estimated value in the next equation, you go on estimating the values of U1, U2, U3, which is called as ordinates of unit hydrograph. And these are all the ordinates. This is how we derive the ordinates of unit hydrograph from a complex storm. Okay, so I request everyone to write down this and solve this. The following table gives the ordinates of a direct runoff hydrograph resulting from two successive 3-hour duration of rainfall excess 2 centimeter and 4 centimeter. Derive 3-hour unit hydrograph. Right. So first thing, normally what we do, the time, see the x-axis is time of measurement. That means rainfall may happen for 6 hours, but still I can measure at every 3 hours. Or rainfall may be happening at every 3 hours. I may be measuring only every 6 hours. So the x-axis, if we make equivalent to our duration of rainfall, then these calculations will become much easier. Okay, so I think I request everyone to solve this and we will see it in the next class. I have given the answer also. You can check it later when I give this PowerPoint to you. Okay, now the third method I have not explained, right? In the third method, the intensity is also different, right? First one is simple storm, second storm only the depth is different but duration is same. The last method very complicated, the depth is also different and duration is also different. That means 5 centimeter in 6 hours, 4 centimeter in 3 hours. Then I cannot apply the principles of superposition. Okay, because when I apply principles of superposition, something should be common. When I apply these principles of superposition, the duration of storm is constant. That is why I do it on principles of superposition. But in the third method, third derivation, that is from complex storm, there is no principles of superposition applicable because the magnitude is also different and duration is also different. This is looks very simple, but there are certain guidelines, right? What is the first one? How will you find this rainfall? Every rainfall happens for 3 hours, 1 hour, or exactly 5 hours? No, it will not. So the duration, somewhere we have to make it to a round figure. So that is the first point, right? Like simple storm and complex storm collection from the data, try to adjust the rainfall within the period of plus or minus 10% of D. That means if I say it is 3 hours duration, it may be between 2 hour, 10% of 3 hours, right? Plus or minus. Okay, then still you can consider that as D hours. Else derive various MD hour duration unit hydrograph and then try to superimpose. Thus, to solve this problem, we need to convert the available D hour unit hydrograph into MD hour unit hydrograph, where M is an integer. Suppose if I have, that's what I told, no, I have 3 hours, then I have to derive unit hydrograph for 1 hour, 1 hour, 1 hour, 1 hour, keep it ready. Right? That means I am reducing 3 hours to 1 hour. But it is not simply dividing all the ordinates by 3. Please remember, because this is not the rainfall to apply my linear response or linear assumption. This is reduction in duration. When I want to reduce the duration of rainfall, then the method is not simply dividing everything by that particular unit. You have to employ a methods. There are two methods, right? The first method is method of superposition, and then second method is called as S-curve technique, right? This method of superposition is applicable only when this in M, which you are using this M, is multiples of D. It's an integer. For example, I have 6-hour unit hydrograph. Now I want 12-hour unit hydrograph. It is not just multiplying by 2 all ordinates. Then the rainfall also should be clubbed, no? Then for 12 hours means it is rainfall of 2 centimeter. Then we have to do certain calculation to arrive MD our unit hydrograph. When M is integer, we use this method of superposition, and we use S-curve technique when M is fraction. That means from 6 hours you want to derive 3 hours. There M is 0.5, like that. Right? We will see one by one. First, let us assume that method of superposition. Right? To solve this method, a D hour unit hydrograph is available. That is a basic assumption. Superimpose M unit hydrographs with each hydrograph lagged by D hours. Right? Then you add all the ordinates. So the ordinates of direct runoff is due to M centimeter in MD hours, because you have added M times. Then to derive the unit hydrograph for MD hours, you divide all ordinates M times duration to derive a 30-hour unit hydrograph, right? That means this is my 6-hour unit hydrograph. I have a unit hydrograph of 6-hour duration. That means what? 1 centimeter. This blue color is the hydrograph. 1 centimeter in 6 hours. Now what I am doing? I am doing the principles of superimposing. That means I need a unit hydrograph for 30 hours. Then what happens? I lag my unit hydrograph every 6 hours up to, right? Now what happens? I added each and every at 6th hour only one. At 12th hour it is first integrograph, second ordinate plus first ordinate. That means it is a cumulative. But you see the rainfall. How many centimeters it is? 5 centimeters. Right? But what I want 1 centimeter in 30 hours. So you divide each and every ordinate of this added value by 5 centimeters. So this black color hydrograph is the unit hydrograph of 30 hours. Just imagine 1 centimeter in 6 hours, how the unit hydrograph will look like, and 1 centimeter in 30 hours. But please note, the runoff volume remains same for 1 centimeter in 6 hours and 1 centimeter in 30 hours, because rainfall excess is same. So runoff depth is also same. So in this case, the area of this blue 6-hour unit hydrograph and area of this black 30-hour unit hydrograph is same. Okay. So I can do this in tabular form also. Method principles of superposition can be done only when my time of measurement is equal to the unit hydrograph duration. So you lag it 4 times. Okay. 6 hours, 12 hours, 18, 24. Then you add all these things, divide it by 5 centimeter, will give you unit hydrograph for 30-hour duration. Okay. We'll come back to this, or only 5 minutes, right? So what happens when MD or unit hydrograph is derived from D hours? See, as I said, this blue hydrograph area and this black hydrograph area is equal to 1 centimeter. How we can compensate? There is a change in shape. The peak is reduced, base time is increased, but the area remains same. Now the second method, that is when my M value is fraction. How to derive the unit hydrograph? That means I have 6 hours, I want 3 hours unit hydrograph. Then we use a technique called as summation curve. That means what? I go on lagging the D-hour unit hydrograph infinitesimal time. That means continuously until my discharge becomes constant. Right? If I add, go on. If I still add one more unit hydrograph, my discharge becomes constant. Now what I do is I call this as summation curve A. Now I lag this summation curve by a fraction required, right? And I have to find the time period at which my discharge becomes constant, right? So this S curve represents the maximum rate at which an effective rainfall intensity of 1 centimeter per hour in d hour duration can drain out from a catchment. Suppose we lag this S curve by md hours and take the difference between these two, right? Now I am lagging it. That means from 6 hours, I lagged it by 3 hours. Now you take the vertical difference at every 3 hours between this SA and SB, right? And then took the difference in the runoff, right? So that is MD hour duration of rainfall for m centimeter per hour. But I want 1 centimeter per hour. So how will you do that? Multiplied with the ratio of MD or D by MD, or you divide that difference by MD by D. Altogether it is nothing but you estimate the vertical distance between SA and SB, divide it by the fraction M. For example, I am showing you this is my 6 hours. I am doing it for 3 hours, right? This is when you draw it using engineering software, it will look like that. When you do it with a graph sheet, it will look like this. So SA minus SB. If your scale is smaller and smaller, at the recession limb, you will have a curvy nature, not a straight line. So take a large scale. Find out the vertical difference at every 3 hours because you want 3-hour unit hydrograph, right? So SA minus SB is this much. Divide it by MD by D, that is 6 by 3 by 6, which is nothing but 0.5. Okay. So this will give you unit hydrograph of 3-hour duration. The same S curve technique can be used for MD when M is integer also, but it's a graphical method. There may be some error at the recession limb. Okay. So SA minus SB, then every 12 hours. Okay. So this is what the unit hydrograph derivation from D hours to MD hours. Both M is integer as well as fraction. But please remember, this is the comparison. It's a comparison between 6 hours, 3 hours and 12 hours. The 3 hours and 12 hours are derived from 6 hours. When I estimate the area of this unit hydrograph, all the 3 area are same, right? So when I reduce the duration, my peak is increased and base time reduces. When I increase the duration of unit hydrograph, my peak reduces and base time increases. Then what is flood hydrograph? What is direct runoff hydrograph? How to derive this concept of rainfall runoff relationship using this hydrograph, that is called as unit hydrograph. Derivation of unit hydrograph from simple storm, complex storm of constant duration, and also converting D hour duration to MD hours, where M is integer as well as fraction. What is the hydrological effect we can see in our hydrographs? So here I have compared 3 different unit hydrograph of different durations. So originally we had only the 6-hour unit hydrograph, which is drawn in red color, and we have derived 12-hour unit hydrograph by principles of superposition, right? That's black in color, and then with S curve technique we have derived 3-hour unit hydrograph, that is blue color. Now what happens? Please remember, all these unit hydrograph, the rainfall excess is 1 centimeter as well as direct runoff is also 1 centimeter. That means you estimate the area of this diagram, each hydrograph divided by area of the catchment, that should be equal to 1 centimeter. But what we have changed is, the change is in the shape of this hydrograph. When the duration is reduced, the hydrograph will have a peak larger and the base time becomes smaller. Similarly, when you increase the duration of unit hydrograph, the peak flow reduces and duration increases. So this is the first graphical relationship between rainfall and runoff. What is the use? The unit hydrographs are used in development of flood hydrographs for extreme rainfall that may be useful in design of hydraulic structures. Second one is extension of flood flow records, right? Like we have done the rating curve. Suppose if you have a unit hydrograph, then you can estimate what could be the direct runoff due to the given high intensity rainfall. The third one is it can be used in flood forecasting and flood warning system based on observed rainfall. But since we have made several assumptions like time invariance, linear response, rainfall is uniformly distributed, constant duration, then limitation should also be large. So the major limitations of unit hydrograph is it assumes uniform distribution, right? So if it is uniform distribution, you cannot expect a cloud very large. So that is why people say that for derivation of unit hydrograph, the upper limit of the area of the catchment is 5000 kilometer square and minimum is 4000 kilometer square. Sir, upper is 5000 kilometer square and lower limit is 200 hectares. The second limitation is intensity of rainfall is assumed constant, right, for the duration of rainfall excess. The third assumption is precipitation must be from rainfall only. Snow melt runoff cannot be satisfactorily represented by unit hydrograph of the method which we have studied. There are other methods where you can still count snow melt also, where temperature also will become a part of it. Then the catchment should not have unusually large storages in terms of tanks, ponds, large flood banks, storages, etc. Because if you have a storage, then it will affect the linear relationship between storage and discharge. So the principles of superposition will not hold good. So these are all some of the limitations of the unit hydrograph. Then the another guidelines, how long the duration of the rainfall in a unit hydrograph. A rough guide for the choice of D hour is we have seen already, right? The another point is the D can be time to peak or time of rising limb. That can be the duration of rainfall, or it may be basin lag, or sometimes best time is 1/4 of the basin lag, or it may be time of concentration. So it should not be more than these three time, the duration. If it is more than this, then the nonlinear concentration, nonlinear concept also comes into the picture, right? Now, this relationship can be derived only for a basin which has observed rainfall and observed a discharge. Suppose if I have a basin which is adjacent to that, or a basin which is hydrometeorologically similar. If I want to derive a unit hydrograph on that basin, there also I need a observed rainfall and a observed discharge. Suppose in that basin observed data is not available, then how to derive? Then what we can, people have started thinking is they took the concept of rainfall runoff relationship from this gauged basin where you have derived the unit hydrograph for D hours. They took it to the next basin to derive the flood hydrograph. But when I am taking it from one basin to another basin, basin characteristics should be left over. So the first graph such is called as distribution graph, first introduced by Bernard in 1935. Unit hydrograph was introduced by Sherman in 1932. So the first distribution graph is, instead of having a duration in x-axis, it gives the units of time, right? 0, 1, 2, 3, 4. Similarly, the y-axis, instead of giving it in meter cube per second, it is estimated as unit volume per interval. That means there are different ways to express this in percentage. the way in which we introduce this in percentage, we have different types of distribution graph. Okay, the first one is Bernard's distribution graph. Right? Effective rainfall is, so I'm just reading this. The distribution graph introduced by Bernard is a variation of unit hydrograph. It is a d-hour unit hydrograph with ordinates showing the percentage of the surface runoff occurring in successive periods. The base period of unit hydrograph is derived into number of uniform time periods. The percentage of surface runoff are drawn as regular bar against time. Okay, so this is a sample 4-hour distribution graph. So the use of distribution graph is to generate a direct runoff hydrograph for a known effective rainfall hydrograph that is exactly the same as that of unit hydrograph. Thus, the distribution graphs are useful to compare the runoff characteristics of different catchments. Right? Now let us do a sample example. A catchment of 200 hectares has rainfall of 7.5 centimeter, 2 centimeter and 5 centimeter. That means 3 rainfall. The average phi index is 2.5 centimeter per day. Now we have to derive the distribution graph. Now the distribution graph percentage of the surface runoff extended for 6 days is given, right? 6 ordinates. Determine the ordinates of hydrograph, neglecting the base flow. So now what I do, I am putting it, this is my rainfall 7.5 centimeter to infiltration loss is 2.5 centimeter per day. So then effective rainfall, that means the rainfall which has contributed to the runoff is rainfall minus infiltration, right? So we have 3 rainfall. Now put it in the table. So this is my time interval 0 to 1, 1 to 2, 2 to 3, that is in x-axis. Average distribution, it is given in the problem 5, 15, 40, 25, 10. And if I add all these things, that will be equal to 100%. That is what the first distribution graph is. So that means this y-axis are derived by dividing the total runoff by dividing the each and every runoff by the total runoff. Okay. Now the runoff due to first rainfall is multiply the rainfall excess with this distribution. That means 5% of 5 centimeter, 15% of 5 centimeter. So I am going on distributing. Then for the next rainfall it is lagged. That means all this distribution should be lagged. So 5 will be next, 1 to 2, 15 will be 2. So it is 0 rainfall, all values of 0. But the third rainfall is after 3 days. So you have to lag all this distribution by 3 days and the 0 will come here. 5% will come exactly on the third day. That is 5% of 2.5, 15% of 2.5 like this. Now you go on adding. So when I add, that will give me the runoff in centimeters. But I want discharge in terms of meter cube per second. So this is 1 day. If I put centimeter, 0.25 per 24 hours, convert that into centimeter per second, then meter per second, then multiply it with the area of the basin. That will give you meter cube per second. Okay. So that is how we estimate the runoff from the distribution graph. So this is I have given a sample calculation at the end. So this is the use of distribution graph. Then the second method of distribution graph is known as SCS dimensionless unit hydrograph. In the previous case, even x-axis and y-axis are not common, it goes on varying. But in SCS dimension unit hydrograph, the x-axis are divided by T by Tp. Okay, so there is only one Tp and you divide it by the time of observed unit hydrograph. It varies from 0 to 5 times or 6 times. But exactly below the peak discharge, it is 1. And in y-axis, the discharge is divided by peak discharge. So then the percentage varies from 0 to 1. And exactly at the peak time period, Q by QP is also 1, T by TP is also 1. Okay. So the difference between the distribution graph and SES dimensionless unit hydrograph is, in Bernard's distribution graph, the x-axis and x-axis value varies 0 to, you will never reach 100% because you are dividing each and every ordinates of unit hydrograph by total discharge, whereas in this case the values are 0 to 1 in y-axis, right? So the coordinates of SES dimensionless unit hydrograph are given in table for developing a synthetic unit hydrograph. For the same hydrograph which we have derived in the previous case, this is the synthetic SES dimensionless unit hydrograph. Sometimes for a calculation purpose, SES has given soil conservation service triangular unit hydrograph. That means I don't bother about the in-between values. We will bother only about the peak values as well as time to peak. So the value of QP and TP may be estimated using a simplified triangular unit hydrograph. The time to peak is nothing but time of rainfall plus half of the time of duration of rainfall, right? And SC also suggested that the base time TB is 2.67 times of time to peak, and peak discharge, everybody knows, it is area of the basin by time to peak into 1 centimeter. 1 centimeter per hour. This 2.8 is unit conversion. So this method is very useful if I don't bother about the in-between values to estimate the unit hydrograph. Right? For small watershed, time to peak is also given as half of the rainfall duration plus 0.6 times of time of concentration. Right? I'm just giving an example. Develop a 30 minutes SES triangular unit hydrograph for a watershed of an area of 50 hectares and time of concentration is 50 minutes. It is direct substitution into these equations. Right? Given area is 550 hectares, which is equal to 550 into 10,000 meters square, or convert that into kilometer square. TC is here, put it in hours, substitute in this TP, right? Then time to peak is half of the rainfall plus, that is 0.75 hours from the starting, and then peak discharge is area in kilometer square by time to peak in hours into 0.208. So this is the peak discharge. Base time is 2.6 times of time to peak. So this is a sample example to estimate SES triangular unit hydrograph. Okay, but in Indian scenario, the Central Water Commission, Government of India, has given a set of guidelines to derive unit hydrograph for various watershed in India for the area ranging from 25 to 500 kilometer square, right? And we call this as synthetic unit hydrograph. It is an empirical relationship to derive the peak discharge. So the peak discharge is 4.4 times of area to the power of 3 by 4. That means I am converting the discharge in terms of area, which is in kilometers square, and peak discharge is in meter cube per second, where SM is slope. When slope is larger, this is the relationship. When slope is flatter, 222 a to the power of 3 by 4 into s to the power of 2 by 3. This is for peak discharge, and sometimes the SM, weighted mean slope, can also be found when you have large variation in the slopes. Each length divided by its ratio, square root of its slope. Then the lag time for 1 hour unit hydrograph is 1.56 by Q by area. This is an empirical relationship. So design purpose, the duration of rainfall is taken as 1.1 time, or the duration of rainfall in that unit hydrograph is 1.1 times of time to peak. Okay. So the time of concentration is estimated using this an empirical relationship given by Cinder, right? Because this Indian practice was developed later, but Cinder has given a simple method to derive a synthetic unit hydrograph. Synthetic unit hydrograph means you derive a unit hydrograph for a basin which is gauged, where you have measured rainfall as well as runoff. Then estimate constants which are regional and apply the similar constant to this constant to a basin which is similar, hydrometeorologically similar, and derive the unit hydrograph for that ungauged basin. So such a method of deriving unit hydrograph for ungauged basin is called as derivation of synthetic unit hydrograph, or SUH. Cinder's method is 1938. Just after 3 years of distribution graph, we got this method of Cinder's unit hydrograph. To derive this synthetic unit hydrograph for ungauged basin, what we need is the basin characteristics. Right? Then I have now two basins. One is a gauged basin, another one is ungauged basin. So Cinder first studied this in Appalachian Islands in US and developed this synthetic unit hydrograph, also called as Cinder's unit hydrograph. What he derived, right? He estimated the parameters of unit hydrograph from the gauged basin and applied those parameters to ungauged basin. Right? So the same Cinder's method, he defined the shape of the unit hydrograph can be drawn when 5 parameters are known. What is that 5 parameters? First one is the basin lag. That means from center of gravity of hydrograph to the peak discharge. Second one is standard duration of the rainfall, D. Third one is the peak discharge, QP. Fourth one is time of base. The fifth is the width of the unit hydrograph at 50% of the peak discharge and 75% of peak discharge. Then we can easily draw this unit hydrograph. And he called this as synthetic unit hydrograph. Now how to estimate all these things? First, you go to the gauged basin, right? In the gauged basin, he derived an empirical relationship between the time to peak and length of the basin as well as length of the water course. If L is the length of the water course and LCA, sorry, L is the length of the basin and LCA is the distance along the main water course flows, then time to peak is a constant CT, a regional constant multiplied with L and LCA to the power of 0.3. And he found that this CT varies between 1.35 to 1.65 in Appalachian mountains. This regional constant CT is the importance here. Then the second estimation he made is time to peak, right? For peak discharge, QP is nothing but 2.7 times of CP is the regional constant for peak discharge by time to peak, and is also found that the base time is 72 plus 3 times of time to peak. It's a empirical relationship. Now we will see one by one. First one, how to estimate. This is a gauged basin. So here we are measuring the discharge at outlet, and he derived the time to peak is CLCA to the power of 0.3. Okay, take this and go to the ungauged basin. Suppose if you know the slope also, then time to peak can be used this empirical relationship. So this CT varies between 0.3 to 6, and if I know the slope, this N varies between 0.38 to in 1.175 in mountainous region, 1.03 for foothills and 0.5 for valleys. right? Now this is now the second estimation is the standard duration of effective rainfall, right, in the ungauged basin is time to peak by 5.5. If it is not a standard duration, that means it is not in full hours, then you have to do a small adjustment to convert that. So that is called adjusted or modified time to peak is estimated time to peak plus the difference between TR and a small tr by 4, where this small t capital R is duration of rainfall in the gauged basin, T small r is duration in the ungauged basin. If I substitute this TR, small tr is equal to TP by 5.5, you will arrive this equation. Then the third one is peak discharge. He estimated the peak discharge is nothing but a regional constant which varies from 0.31 to 0.9 into area of the basin by adjusted time to peak into 1 centimeter. That is missing. That is why say unit time step, unit rainfall excess. So Q is discharge per unit area, capital QP by area. Now base time is 72 plus time to peak or 5 times of time to peak from the start. You can select whichever is better after drawing the unit hydrograph. Now the width of the unit hydrograph at 50% of the peak discharge and 75% of the peak discharge, he gave an empirical relationship W50, that is in hours, is equal to 5.87 by Q to the power of 1.08, where Q is the discharge per unit area, that is peak discharge QP meter cube per second divided by area in kilometer square. Substitute this, find out. Now I got 1, 2, 3, 4, 5, 6, 7 points in this unit hydrograph. Combine these 7 points to draw a synthetic unit hydrograph. Right? Now let us do it with a problem. There is a two catchments. Catchment A is gauged basin, where I know all the rainfall. I have a hydrograph for catchment A. Now I need to derive a catchment for B. For a catchment, a 2-hour unit hydrograph was developed and was found to have a peak discharge of 50 meter cube per second. And the time to peak from the beginning of the rainfall excess is 9 hours. Determine the elements of 2-hour unit hydrograph for catchment B. So in catchment B, I don't know what is the discharge. Right? Now what we do first for catchment A, right? Time of rainfall, capital R is 2 hours. So my time to peak from center of rainfall excess to the peak discharge is 8 hours. Okay, this is estimated. Now second one is adjusted time to peak in the ungauged basin is 7.857 hours, almost similar. So the time to peak is same for both the basin. Now use the equation to find out regional constant Ct. In this, time to peak is 7.85 and L is 30 kilometer, LC is 15 kilometer to the power of 0.3. Now regional constant Ct is 1.257. Take this to the ungauged basin. Now peak discharge QP is equal to 2.78 CPA by TP dash. So TP dash is 8 hours. So in this only unknown is CP. Now estimate the CP from this. Now these two regional constants CT and CP are taken to the catchment B. Right? See CT and the CT. Now estimate TP of this ungauged basin. So I know only this L and LCA 1.2. So 10.3 hours is the time to peak. But what is the standard duration of rainfall? TP by 5.5, 1.88. So there is a difference of, it's not a round figure. So you can estimate the adjusted time to peak, right? Then adjusted time to will become 10.37 hours. Now peak discharge QP is equal to 2.78 CPA by time to peak. So peak discharge is almost 62 meter cube per second. Now width at 50%, QP is 62 by area is 400 kilometers square. So 44 hours, and width at 75 is 25 hours. Time base 103 hours in one estimation, another estimation is 58 hours. Considering the values of W50 and W75, noting the area of catchment B is rather small, time to peak of 58 hours is sufficient. Right? I have given one more calculation. You can just solve this, find out the values of unit hydrograph for catchment B. Right? So this is synthetic unit hydrograph. Whatever it did, what will happen to the shape of the unit hydrograph when the rainfall is instant? That means rain has fallen with no time. That means duration tends to 0. That means here you can see this is unit hydrograph of D hours. Then I am reducing the D hours. So finally there will be a time when time tends to 0. That means the duration tends to 0. That shape of the unit hydrograph is called as instantaneous unit hydrograph. Actually, when time is 0, the rising limb will not be there, and the recession limb will start from the y-axis and it goes down to 0. It means suddenly there is an instantaneously a discharge of peak discharge. Then how the runoff goes? That is what instantaneous unit hydrographs are. Right? The limiting case of unit hydrograph, 0 duration, is known as instantaneous unit hydrograph. There are several methods, but by definition instantaneous unit hydrograph is fictitious, or we can call this as a conceptual unit hydrograph, which represents the surface runoff from the catchment due to instantaneous precipitation of rainfall excess of 1 centimeter. There is no duration here. Now considering there are several methods. This is a graphical method and others are conceptual method. In graphical method, consider an S curve designated as S1 derived from D hour unit hydrograph. In this, the intensity of rainfall excess is 1 by D centimeter per hour. S2 is another S curve intensity of I centimeter per hour, and S2 is separated by S1 by a time interval delta T or dt, and the ordinates are subtracted. This is same as what we did for S curve technique, and then divide it by dt by D hours. Altogether it says that it is nothing but the slope of the S curve will give you the instantaneous unit hydrograph. This is a graphical method. The other methods, this is a continuation of graphical methods. As dt is made smaller and smaller, dt tends to 0 and IUH results. That means mathematically unit hydrograph, the instantaneous unit hydrograph ordinates is nothing but S2 minus S1 by I into dt. S2 minus S1 will become, there is no difference. It's a small difference in a given delta T. If I is equal to 1, that means instantaneous intensity of rainfall is equal to 1 centimeter, then the ordinates is nothing but ds by dt, which represents the slope of my summation curve. Thus, the ordinate of instantaneous unit hydrograph at any time t is the slope of the S curve of having intensity 1 centimeter per hour. Normally it is 1 hour duration. The other methods which are very famous is Clark's model and Nash model based on concept. Right? Nash model is very useful, and I am not going to explain much about this Nash model. When you come to our postgraduate level, you will understand this Nash model. Right? I have given a simple uses of unit hydrograph. Unit hydrographs are very useful to estimate the flood. For example, in this case, the ordinates of instantaneous unit hydrograph of a catchment are given below. Derive the direct runoff due to a storm of 4 hours and having a rainfall excess of 5 centimeter. Right? I put it in x-axis. in a tabular form. This is the time and this is the ordinates of instantaneous unit hydrograph. Now there are duration of 4 hours and having a rainfall excess of 5 centimeter. Okay. Now this is lagged by 1 hour. Then this will give you the ordinates of 1 hour unit hydrograph. Now if I want it for 4 hours unit hydrograph, draw an S curve, then lag the S curve by 4 hours, the difference. This is the SA minus SH. That will give me the direct runoff hydrograph for 4 centimeter in 4 hours. Then ordinates of 4 hour unit hydrograph divided by 4. So direct runoff due to 5 centimeter is multiply each and every one by 5 centimeter. That means in derivation of flood hydrograph from instantaneous unit hydrograph is first you have to derive the unit hydrograph of d hours duration, right? Because what you have instantaneous unit hydrograph is assumed as for every 1 hour. So convert that into 4 hour unit hydrograph and then from the 4 hour unit hydrograph apply the principles of superposition, multiply it with the rainfall excess will give you the direct runoff for x centimeters. So it is a two-step calculations, right? So with that I am winding up the hydrograph class.